Well, welcome back for a new week of Calc 2. This week is all going to be about geometry and using integration to find areas and to find volumes. The first thing we're going to have to explore, though, is sometimes when we're asked to find these geometric shapes or measurements, it's easier to integrate with one variable than the other, and sometimes it's necessary. So we're going to practice switching our perspective to think about how do we integrate with respect to the other variable. So let's start with a problem familiar to us. We're going to look at finding areas under the curve. And I've prepared a problem for us. So we're asked to find the area enclosed by the line y equals 3x, which is here. The quadratic y is 4 minus x squared, which is this curve going down, and the x-axis. This means that we're looking at this region right here. Generally speaking, when we've done this before, we've done it in such a way that the area we were looking at was kind of trapped between the two curves, one below and one above. This region doesn't have that property. What we can do, though, is we can split it into two regions. One where we're going to have the area below the line, and then we can add the area below the quadratic. So we could say the area under the curve A is going to be the integral from 0 to 1 of the line function. So the area under 3x dx. And then we have to add the area that's below the quadratic. So that area goes from 1 to 2. And the function we're integrating here is 4 minus x squared dx. And so we go through and we compute the area. So the integral of 3x is 3x squared over 2, evaluated from 0 to 1, plus the integral of 4 minus x squared is going to be 4x minus x cubed over 3. And we're going to plug in and evaluate from 1 to 2. So when we plug in 1 right here, we're going to get 3 halves, minus 0 when we plug in here, plus. When we plug in 2, we're going to get 8, minus 8 thirds. And then we're going to have to subtract when we plug in 1. That's going to be 4 minus 1/3. I think I need one more parenthesis to close it off. So I get 3 halves. 8 minus 8 thirds, so 8 is 24 thirds. Minus 8 thirds is going to be 16 thirds. Minus 4 plus a third. So I'm going to have 3 halves minus 4. That's just going to be what? 8 minus 4 is 5. So negative 5 halves. And then here I'm going to have 16 plus 1 is 17 thirds. So over 6 is going to be my common denominator. I'm going to have 2 times 17 is going to be 34, minus 15. And so I'm going to get, looks like, (19)6. OK. So we find a total area going from 1 to 2 of 19/6. And this is what you already know how to do. There's nothing new here. I'm just wanting to be careful that I'm not making any addition mistakes. But I think I'm OK. If you find something incorrect in the computation, please post it in chat, tell me who you are, and I'll give you some homework extra credit points. Now, the new way, what I really want you to pay attention to is this. Let me erase the computation, and we're going to switch our perspective. And instead of viewing this as a region that's bounded by two curves, I'm going to see it as a region bounded by curves this way. And so I'm going to have a top curve of right here, y equals 4 minus x squared, and a bottom curve of y equals 3x. But I'm going to view them where x is a function of y. And so I'm going to want to be taking these lines and adding them together this way as my y value changes. And every time we add the y's together, these line segments, we end up with the actual whole area that we're drawing. So to do this, we're going to change the equation to become, well, we solve for the other variable. So y equals 3x becomes, dividing both sides by 3, x is going to be y over 3. And similarly, y equals 4 minus x squared, we're going to solve for x. So we're going to subtract 4 from both sides. Negative x squared equals y minus 4. I'm going to divide by negative 1 or multiply. X squared equals 4 minus y. And then I'm going to take a square root. X will be the square root of 4 minus y. And now I can view this exact same area as the area that's trapped between the upper curve and the lower curve. And so I'm integrating the difference between the curves, giving me this line segment difference every time, and adding all of them up. And so I get my area shaded in red is now going to be the area where y goes from 0 to 3. So y is now our variable of integration. So we integrate from 0 to 3. My top function is the one that is furthest away from the x-axis. So that's going to be my quadratic. So my quadratic is now the square root of 4 minus y. And then my lower curve is the straight line, y over 3. And we are integrating dy. Notice that everything now is just expressed in terms of y. So we have set up our area as an integral dy, and we can go ahead and integrate. So an antiderivative of 4 minus y, well, we're going to need a u substitution here. So u is going to be 4 minus y. So du will equal negative dy. So we can just multiply both sides by negative. So dy is negative du. And u of 0 is going to be 4. And u of 3 is going to be 1. So now we have our bounds for this first piece. The second piece, we won't need a u substitution, so we're going to do it separately. So for the first piece, we're going to be doing the integral from 4 to 1 of root u negative du plus the integral from 0 to 3 of negative y over 3 dy. The antiderivative of root u is u to the 3 halves over 3 halves. And we have a negative in front, and we're evaluating it from 4 to 1. Minus the antiderivative of y is y squared over 2. So we're going to do a y squared over 2 times 3, which is 6. And we will evaluate from 0 to 3. And now we're just going to plug in subtract. And you'll notice that you have this square root, but because we have like 1 and 4, those square roots are perfectly whole numbers. And so we will, in fact, get the same result we got in the previous computation. I'm going to go ahead and let you plug this in on your own. And I'm going to ask you that if it doesn't come out to the same thing you just did, post that in the discussion chat for this week. And I'll put up a short little video within the discussion to see if we can resolve the differences and make it work from here. So it doesn't look like we saved enough time here, but really I just wanted to illustrate that integrating with respect to y is very similar to integrating with respect to x. You just have to shift your perspective because now you're slicing horizontally and you're adding those things as they stack up. You're going to be asked to do this in the exploration this week. And there are methods of computing volume that ask you to integrate with respect to y or with respect to x, depending on where we are rotating things about. So with that being said, I will say see you later and into the next video.